So this video is going to be about stereoisomers. Now we have done isomers in another video before this. In that video, we kind of gave you a definition of isomers and then talked about constitutional isomers, which was one class of those isomers. My focus today would be on another class of isomers, which go by the name of stereoisomers. Let's begin with what are isomers, just to quickly review some old stuff and see if we remember things before we move on to something new. So isomers are compounds that have the same molecular formula but are structurally different. They have the same molecular formula, but they are structurally different. Now, isomers were classified broadly into two types. One was constitutional isomers, and I've made a video on this before, where we also introduced IUPAC nomenclature with the help of constitutional isomers. So you can look that up if you need to review this. The other type goes by the name of stereoisomers. Stereoisomers can again further be classified into geometrical isomers and optical isomers. Optical isomers is a pretty big chapter that I would like to break down into shorter concepts and do multiple videos on it on a later day. But today I would like to concentrate on geometrical isomers. Geometrical isomers, we would learn two types of geometrical isomers, the cis-trans type and the E and Z type. So I would be focusing on cis-trans and E and Z type, which are both geometrical isomers, which are a type of stereoisomers. So these words in boxes, that's the pattern I'm going to follow today. We'll talk about what are stereoisomers, what are some geometrical type of stereoisomers, and specifically concentrate on these two types. Okay, what are stereoisomers? So the last part of the name says isomers. So whatever definition was true for isomers, a part of that definition must be true for stereoisomers as well. So stereoisomers are compounds that have the same molecular formula, but their arrangement of atoms in space is different. So arrangement of atoms in space is different. What does that mean? Let's look at some examples, and I'm sure things would start making more sense when you actually see examples. Let's start with the cis-trans type of geometrical isomers, stereoisomers. So for the cis-trans type of isomers, let me give you the structure of a compound and explain with the help of that. So the word cis in Latin means this side of. This side of. And I'll leave a little space so that I'm able to draw something out for you. The word trans, again in Latin, would mean other side of. So cis-trans isomers are best drawn with the help of alkene type of molecules. Alkenes would mean I have a CC double bond. So in one of these compounds, let me draw a CH3 group on one of the carbons. The other side could have a hydrogen. Remember, carbon has 4 bonds around it. So 1, 2, and then 3 and 4. For the other molecule, I could have another CH3 and H. So I should have a group of like atoms or cluster of atoms. What does that mean? I have both of these carbons having CH3 and H. The other one also has a CH3 and H. So these are like groups, so are those. So like groups is important. Groups of the same type is important. So since the word cis means this side of, what it portrays is these same type of groups, the methyls in this case, are on the same side of the double bond. So when you determine if something is going to be cis or trans, stop at one carbon atom at a time. So I would consider this to be carbon 1. I would consider this to be carbon 2. I'm labeling them just so that I can follow them around. Carbon 1 has a methyl and a hydrogen. Carbon 2 also has a methyl and a hydrogen, so like groups. Now, both of these methyls on the 2 different carbons are on the same side. Both the hydrogens are on the opposite side, but again, same side with respect to each other. So this would be an example of a cis type of molecule. I could have also done a carbon-carbon double bond. I have a bromine. I have we could do a methyl. A methyl group is also written as Me. If I have to draw the cis form on the other carbon, I should have like groups on the same side. So bromine on the side that bromine is for the other carbon, and then methyl on the side that methyl is for the other carbon. So that would be an example of a cis type of molecule. A cis type of molecule can also be drawn on a ring compound, like a cyclic compound. So I could draw a cyclic molecule. In this case, I'm drawing a cyclohexane. Each carbon should have 2 more bonds. So I'm drawing 1 bond here, 1 bond there. 1 bond here, 1 bond there. We could draw an iodine, and I could draw an ethyl. Same here. I could draw an iodine on the same side and an ethyl on the same side of the other ethyl. So again, like groups, the constraint is you would have to have them on the same side of a locked system. See the double bond here? That serves as a lock. I'm not able to move these around. I can't just turn this carbon and make the green group appear here and the white group appear there. That is not going to happen. I can do that at the cost of breaking this bond, breaking that. Either I can break this and turn it, or I can take this out, and then switch their positions. So the double bond here works as a lock. If you want, you can make a cyclic molecule. It's a little more time consuming to make a cyclic molecule during a lecture, and would be kind of boring for you to watch me make a cyclohexane the whole time. So I leave it up to you to make the cyclohexane molecule, attach these groups. You don't even have to make these groups, just color code them. Like I used a green and another green. So those kind of are symbolic for same groups. 2 whites symbolic for same groups. So you could just color code, maybe use 2 yellows for the iodines, and then 2 other same colors for your ethyls. And then turn the carbons that are holding these groups, hold them and try to turn the molecule and see if you can flip and bring these to the other side. You would see the ring also acts like a lock, and you can't move things around. Now, what would be the trans form of the molecule? Maybe we can draw the trans form of all 3 of these. And if this was a live lecture, I would have loved to hear your take on this. But since it's not, I'll give you the answer. So one side we can keep the same. For the other side, remember it has to be on the other side of the like group. has to come on the other side. So if methyls on the top side of this double bond, for the other carbon, that methyl should be on the bottom side of that double bond. And then here, the hydrogen should go in. This is the transform of the molecule. If I want to go ahead and draw this, again, you can choose which side you want to keep consistent. I choose this time to keep this, the right carbon consistent. So Br on the top, methyl on the bottom. If I want the transform, I would have to switch the methyl to the top, Br on the bottom. If I want to draw the ring version of things, I would draw the ring as it is. And then 2 bonds here, 2 bonds here. I this time wish to keep this iodine and ethyl as I drew it the first time. Since it's the transform, iodine should be here, ethyl should be here on the other carbon. So this is cis-trans type of naming for these kind of alkenes. Since they are isomers, remember they should have the same molecular formula. So the things you have used to make them should be the same. Like if I compare these two, both of these should read as CH3CH, double bond CH3, CH3CH, double bond CH3. So if I were to write down the condensed form of this molecule, I would write it as CH3CH, double bond CH3. And I would write the exact same thing here, CH3CH, double bond CH3. However, they are not exactly the same thing. They are structurally different. When I draw this out, and it's more of a, complete structure form, I can see the arrangement is not exactly the same. The arrangement of these groups is different. On the first one, I have the 2 methyls on the same side. On the second one, I have them on the opposite side. Does it matter? Yes, it does. You have learned about intermolecular forces in Gen Chem, which you are supposed to have taken before organic chemistry. So think about this molecule. Bromines are more electronegative. So I have a net dipole moment of these shared electrons being pulled in the direction of the bromine. On the other side, again, between carbon and bromine is more electronegative. So yes, these electrons are shared, but bromine is pulling more. So for this molecule, I have a net dipole moment that's in that direction. For the transform, I actually have these dipole moments that are equal, but opposite in direction. So for this, the dipole moment should cancel out and be 0, which is not true for that one. So the solubility of these 2 molecules would be different. It could also affect their physical properties. So cis-trans isomerism of a molecule with the same structural formula does matter. It's important. All right, what is the Z and E type of nomenclature? So this is the first thing we did today. I would have to move to a new page to talk about the Z and E nomenclature. So for the Z and E nomenclature, I think it's important to kind of tell you what those alphabets even mean. Where did they come from? So here is the Z and here is the E. Again, I left some space so that I can draw some molecules. Z comes from a German word, Süßemen. Süßemen. It's a German word, Süßemen, which means same side. E is also a word of German origin, and gegen, and this just means opposite side. So if we go back to the previous page where cis meant this side and then trans meant other side, and then if you compare it with Z and E, Z would mean same side, E would mean opposite side. They are kind of saying the same thing. Again, for Z and E, Z is a case that looks very similar to the cis form, where two things that I am kind of looking out for would be on the same side of the double bond. And with with E, they would be on the opposite side of the double bond. But the only difference is that this time I would not be able to find like groups. When it was like groups, it was easier for me to spot. I could just, after a couple of examples that a student sees, they would not even have to, sit and decode things. They can just look at a molecule and see, oh, these are on the same side. Oh, these are on the opposite side. So this must be trans, that must be cis. But if I don't have like groups, then how do I know if it's going to be cis or trans? And then should I actually call them cis or trans, or should I use some other type of other way of naming them? So here is my CC double bond. So that's my lock. I'm not able to rotate those two carbons and move things around. So on the first carbon, we could put in some group of our choice. We could do maybe a halogen. I can do a Cl on one side. On the other one, I could do, on the other side, I could do NH2, which is an amino group. On the other carbon, I could do an OH, that is an alcohol, and H. And I'll try to do another lecture on functional groups, which is how do you know this is called an amino group? How do you know this is called an alcohol group? How do you know this is an alkene? All of those I can address in that lecture. So with a molecule like this, yes, I see a CC double bond. I could call this carbon 1, I could call this carbon 2, but I don't see any like groups. So how am I going to decide if this is the Z form or the E form of the molecule? Also, just so you know, if I'm not doing UPAC nomenclature in one of my lectures, I just randomly number my carbons to be able to follow them along and refer to them by a name. I'm not necessarily numbering them in the correct UPAC numbering system, just so you know that. So I want to call this my carbon 1. I'm calling this my carbon 2. So I would stop at carbon 1 and see what's attached to carbon 1. Carbon 1 has a chlorine and a nitrogen. So my carbon 1 has an attachment to a chlorine and a nitrogen. Now, we would be using a rule that tells you which of these groups has a higher priority. And the way the rule works is you look at the first point of attachment. So the first point of attachment here is of Cl versus N. The atom that gets the higher priority out of those two is the atom with the higher atomic number, not mass number, atomic number. So out of Cl and N, Cl has a higher atomic number. Hence, Cl side wins. So this is the higher priority group. So again, stop at both of these positions. Look at one atom at a time. Again, please do not look at the whole thing and add everything up together to determine the atomic number or mass. That's not the rule. The rule is one point of attachment at a time. Cl versus N. Whichever has higher atomic number, that's the side that wins. So I could have NH2 followed by, 10 carbons here to make a long chain here. Doesn't matter. This side is still going to win because your first point of contact is a Cl versus a nitrogen. Cl has a higher atomic number, hence this side wins. So this is of higher priority. This rule goes by the name of Kellogg-Ingold priority rule. So let's try this on the other side. On the other side, I have this C2 carbon. The C2 carbon directly attaches to oxygen versus hydrogen, directly attaches to oxygen versus hydrogen. Who has a higher atomic number? Well, oxygen wins. So this is the side that wins. So both my higher priority groups on the two carbons are on the same side of the double bond. Hence, this is a Z type of, it's the Z form of the alkene. If I want to draw the E form, now that I have the Z form drawn already, it would be easier for me to just look here and draw the corresponding E form. So here is my carbon-carbon double bond. Again, it's your choice if you want to keep this side consistent or the other side, just hold on to one. I want to keep my Cl where it was and NH2 where it was. I know this is my higher priority group. So on the other one, I should draw my OH here and H here so that the two higher priority groups are on the opposite side. So determine priority using your Kellogg-Ingold priority rule, and then higher priority groups on same side, call it the Z isomer. For the other one, when your higher priority groups are on the opposite side, are on the opposite side, I would refer to it as the E form of the molecule. Again, consistency-wise, they both have the same molecular formula. I have two carbons, one chlorine, one amino group, one OH, one hydrogen, one hydrogen. So molecular formula completely matches. What is different? Arrangement of atoms in space is different. On one, I have the Cl and OH on the same side of the double bond. On the other one, I have the Cl and OH on the opposite sides of the double bond. Again, when you look at higher priority groups, you look at what is attached to one carbon at a time. So you start with this carbon, look at what is attached, determine which has a higher priority, and then you stop at the other carbon and do the same thing. Let's do maybe two more examples, just for fun, just to make sure we understood. So like two practice kind of problems to just see if we are able to determine E or C, or maybe we should even start with cis-trans and then do E and Z. So these are just practice type of problems. So I will give you a CC double bond, and on one side I give you a CH to CH3, which is an ethyl group. On the other side, I give you a CH3, and then for the other carbon, I give you two CH3s. Will I be able to call this any of the ones that I learned before? Cis, trans, E, Z? Well, let's find out. Let's do one carbon at a time. So I stop at carbon 1. Again, I'm not following UPAC nomenclature numbering rules. I'm just numbering them so that I can call them some name. So this is my carbon 1. Carbon 1 has two of the same groups. How do I even know which has higher priority? So in a case like this, I am not able to assign cis or trans or E or Z. So this cannot be categorized into any one of those type of stereoisomers that you just learned. So cannot assign cis or trans or E or Z. Let's try another one. We could do carbon-carbon double bond. Let me keep one part the same. And I wish I could ask you to suggest what else can I do to draw maybe a corresponding cis type of molecule. Well, if I'm trying to draw the cis form, I should have like groups on the same site. If I am trying to draw a trans type of molecule, I should have like groups on opposite side. Again, having like groups is important. So these should both be methyls, and those should both be ethyls. Then only you can refer to them as cis and trans if those are on the same side. they are cis. Those are on the opposite side. They are trans. Now let's give drawing E and Z a shot. So I would again start with my CC double bond. On one, I'll just come up with something. Maybe we can do a C attached to two other C's and fill out the rest with hydrogens. So 2 hydrogens here, 2 hydrogens here, 3 hydrogens here. On here, we could do a CH3. On the other side, I could do an iodine versus a chlorine. Am I able to spot like groups? No. So then just let's try to use the priority rules. Again, not following UPAC nomenclature numbering rules, I will just call this 1 and carbon 2. Let's start at carbon 1. Priority rule says, go one place at a time, one atom at a time. So my first point of contact is an iodine versus a Cl. My first point of contact is iodine versus Cl. Who wins? Iodine has the higher atomic number. Again, atomic number. So this is the one that wins. This is the one that wins. Now I'm at C2. What is my first point of contact? I have a carbon versus a carbon. Both of them are carbons. I can't decide. Well, let's see. If you can't decide based on the first point of contact, move on to the next point of contact. So wherever you are able to find that first difference in atomic number will help you make a decision. I wasn't able to make a decision based on the fact that C2 is connected directly to 2 carbons. So they're both the same. So let me just keep moving on. This carbon, so maybe what I can do is I can put a little asterisk on this carbon so that you are able to understand which carbon that one is. So this is the asterisk carbon and this is the other one. So the carbon with the little star on it, that is attached to 2 hydrogens and another carbon. So this is attached to 2 hydrogens and another carbon. The carbon that does not have the star, that is attached to what? 3 hydrogens. Hydrogen, hydrogen, hydrogen. Can you spot the difference? So the difference lies right here. This carbon is attached to hydrogen, hydrogen, carbon. The other one is attached to hydrogen, hydrogen, hydrogen. Can't compare using this, can't compare using this, but I can compare using these. This has a higher atomic number than that one. So this is the group that wins. Again, I would strongly recommend not to just look at the size of the group and determine. That could lead you sometimes to a wrong answer. Like with this one, it worked out that whichever visually looked bigger turned out to be the higher priority group, but that's not always going to be true. For example, the amino group example that I was giving you, maybe we can do one last one with the help of that. I could put 10 carbons after this. Would not matter. It's Cl versus N. So how big or small this group is would change the atomic mass. But my rule says, the Kellogg-Ingold rule, it tells you that it's the first point of contact that matters, that helps make you take a decision. So this is my point of difference. So that is the higher priority group, both higher priority groups on the same side. This must be the Z form of the isomer. Let me do one last one with you. We could do a CC double bond. I could have, I'll try to make it very similar looking to the last example that we did that I just brought up. I had one Cl on one side, and on here, let's do a CH2, maybe another CH2, and then NH2. And let's see if we can compare. So I'm looking at this carbon first, followed by this carbon. On this carbon, first point of attachment is a Cl versus a C. Cl has higher atomic number, wins. Doesn't matter how big this part is. It's about the first point of contact. On the other one, it's about oxygen versus hydrogen. this wins. This is also a Z type of isomer. If you wanted to draw the E form of this molecule, you would keep one side the same as the Z form and then switch the other side around. I hope you got a little feel of what are cis and trans type of isomers and what are E and Z type of isomers. Well, definitely let me know. If you need help with more problems, we can do a little session and discuss that. Also do let me know if you want to hear some other specific topics.